Hi, James.
Hello, it's good to see you again.
I'm very glad to see you again too. How do you find parallel developer over the world? How you describe a typical parallel developer?
A typical parallel developer. Well, I think there are kind of two types. There are people who have been doing parallelism for a long time in the high performance supercomputer area, and they've always emphasized performance over everything else. Spend a lot of time on it, whatever it takes, get the most out of the hardware. What we've seen though after the introduction of multi-core is the emergence of a different type of parallel programmer. A programmer that doesn't think of themselves as a parallel programmer, they think of themselves as a programmer. They've got a job to do. Now their applications are running on multi-core, and the question is, how do I get the benefits of multi-core without changing everything, without being, an extremist? And that's where a lot of our emphasis has been the last 4 or 5 years, is about bringing new things to market, new capabilities in the tool to let people who have an application and want to take advantage of multi-core take advantage of it. So I would say increasingly the typical parallel programmer, because of multi-core, is someone that has a job to do, and occasionally parallelism is useful in parts of their program to get that job done, and they use it and they use the tools to accomplish that, like they use any other tools to make their application work. But they don't think of themselves as a parallel programmer like people working in HPC think of themselves as parallel programmers. I think the new parallel programmer, the typical one, is a programmer that just has a job to get done and happens to use parallelism tools sometimes.
Okay. Can you give us your favorite Intel parallel library, and can you justify this choice?
Wow. I think the answer is going to be Intel threading building blocks. I've been associated with this project a long time. I describe myself as a C programmer that knows C++ pretty well, so living that C and C++ world, I have a love for elegance and efficiency. Threading building blocks gives me access to that performance in an elegant fashion, very deployable. And the other thing that really makes it a favorite of mine is that it's caught on so much. It's more popular than OpenMP for getting parallelism, which is saying a lot, because OpenMP has been around 15 years and threading building blocks has been around about 5. It's used by really important software. Of course, we were fortunate that Autodesk Maya adopted us very early, but just in the last year, Adobe's Creative Suite 5 uses threading building blocks. Some of our favorite movies from DreamWorks Animation, Intel threading building blocks is used at DreamWorks Animation as their method of getting at parallelism. The list is on and on and on. So as an engineer, I love that our product's being used. But I got associated with it because I love the elegance, the performance, wrote a book about it, and the usage of it has just come on and encourage that even more. But as you know, Intel threading building blocks, as much as I love it, there's so many other cool things we're doing too, because I don't think any one solution solves everything. But for a C and C++ programmer like myself, the Intel threading building blocks is a clear winner.
And I suppose you really enjoy the new lambda extraction in C.
Yes, I honestly, I look back at teaching threading building blocks without lambdas, and I hate it. Lambdas make it a lot easier to teach. They make the expression of a task simpler to read. So yeah, I'm a huge fan of lambdas.
And if you have some advice for a TPL programmer who wants to go to C++, it's not usual, but sometimes, as you said, during your job you need to do some C++ code. Which advice can you give us between PPL and TBB? if I need to use both, or because in TBB there is a memory manager, very useful.
Right.
And what is your position about that?
So you know, PPL from Microsoft, which does C and C++, TPL that does .NET, Intel's threading building blocks for C and C++. The common thing they all share is this philosophy of task-based programming, which is really important. So once you get your head wrapped around that, as a programmer, you'll understand how to program. So if you start, as you said, with TPL on .NET, you have a very rich set of some parallelism constructs built on this idea of task parallelism. So if you were to be doing C and C++ programming, you can compare TBB and PPL in the following ways. PPL is richly supported by Microsoft. It's Windows only. TBB, of course, is available on many platforms. For me, in my experience, that's the first decider for people. If you need a solution that works on anything other than Windows, TBB is an obvious choice. The other thing, PPL has a more limited set of functionality than TBB. In the algorithms, we have some more algorithms. We've got some pipeline capabilities. We've got scan. They add to the complexity of TBB a little bit, but I like to think of it as richness. Microsoft has kept PPL a little bit simpler. You know, depending on your needs, that may or may not matter. We do have a thread-aware memory allocator in TBB. Some of our customers, that's the first thing they use. Everybody does memory allocation. If you have a parallel program, a thread-aware memory allocator can be a big boost, and you can just replace malloc, or you can replace in C++ the new functionality to use that. But you know, you can use that with PPL. You can use our memory allocator with PPL. So as compelling as that is to look at TBB, if you're still willing to be Windows only and the PPL algorithms do your thing, you can use the TBB memory allocator. So it may not have been a real strong answer, but I think the key thing is once you look at task-based programming, you've learned the most important things about parallelism, and today you have a rich set of choices: TPL on .NET, PPL on Windows, Microsoft, TBB on Windows and other operating systems. You won't go wrong using any of them because they're moving you in the right direction of using task-based parallelism, and moving between them is actually quite easy.
Okay. Can you explain the frame-based analysis in VTune-XZ?
Yeah, it's a frame-based analysis in the new VTune is a favorite feature of mine because I think it's just so innovative. It's a type of performance optimization that's been there forever, but now we have it in a tool that can help you with it. And opens up exciting new opportunities. So what it is VTune has traditionally always helped you see where your program's spending time, and you spend too much time or something's happening and you want to optimize it, make it run faster. But that generally causes people to just make their program run faster, arbitrarily. And usually we think, well, if my program runs faster, it's good. But it turns out that a lot of optimizations, what you really want is to optimize to fit within certain time constraints. And we call it frame-based somewhat as a reference to playing back images. So the example I like to give is if you have a video playback, you might be playing back something like 30 frames a second. In that case, all you really want is every frame's decode to happen faster than 1/30th of a second. You don't want to just speed up, if you have jitters in your video playback, you don't want to just speed up everything 10% or 20%. What you really want to speed up are the frames that are taking too long. So what VTune lets you do, using this as an example, is you can say, well, here's the beginning of a frame decode and here's the end. And then what VTune will keep track of is every frame operation that happens, and you can sort and say, I want to look at the frames that took the most time. And okay, now I'm looking at the frames that took longer than 1/30th of a second, and I want you to only show me data that came from those frames. Disregard the rest. And suddenly then you're looking at things like cache misses or TLB misses or time spent in different functions, but you're only looking at what happens when the frame took too long to decode. And then every decision that causes you to make about changing your program will benefit the frames that are actually causing you a problem. Now, this is applicable to a lot of things. Video playback's an excellent, easy to understand example, but there's many different applications where improving the performance of the outliers so that you can fit within a time constraint, maybe it's real-time response, or maybe it's improve the scaling of a parallel algorithm. There's many times where you really want to understand what's causing the outlying performances, not just the general overall. Because if you look at video playback, maybe one time in 20,000 you're getting a TLB miss, so that's not very, or that's actually would be pretty extreme, but a cache miss would be a better example. That's not very extreme. But if that cache misses are consistently happening and causing a frame to not decode fast enough, you care. So the frame-based analysis in vTune lets you tag different parts of your code, the beginning and end, and then you're able to sort and then look at only the data collected in the outlier cases. Very, very powerful new feature.
As expert, what is your position about GPU vs CPU in parallel world?
So the most power out of parallelism comes when you have a bunch of very capable, flexible CPUs connected together. So GPUs are exciting because they can handle certain types of data parallelism efficiently, but they have a challenge. They're fixed function hardware. They have some flexibility, but they're designed to be a GPU, not to be general compute. And because of that, you're trying to force computations through them. And in some cases, the computations map well, in others they don't. And it sets up a little bit of what I call a fragile environment too, in that the hardware is good at something, it's not good at the general purpose. So if you stray a little bit out of what it does well, you suddenly fall off a performance cliff. So a better solution is something more general purpose, more programmable, but that has its own challenges, building it, deploying it. But I think that is the future. That's why I'm so excited about our Mike architecture from Intel, which is a very high core count interconnected set of x86 processors. I think that will prove to be more flexible so that one can program at a higher level of abstraction, and your programs can last a longer time and map onto this hardware more easily. Because today, if you look at the most popular methods of programming a GPU, you're looking at something like CUDA, or you're looking at the promise of OpenCL, which looks exciting, but we're talking about very low-level programming models that excel at being close to the hardware and having no overhead. But that no overhead is very attractive, but the complexity of building a program that close to hardware and debugging it, it's a challenge. That's where we are today, but as we get more flexible hardware, we can get more flexible programming languages, we can be programming in something more familiar, more high level, and yeah, it comes with some overhead. I mean, let's be honest, the most popular programming languages today all have overhead, and Java's taken the world by storm for the last 15 years, and it has a lot of overhead, but yet it's more programmable. People that talk to you about Java don't sell you on its overhead as a function, they sell you on its ease of use. And if we look at programming models that can be done with C and C++, a certain amount of overhead, but yet you do that because the programs hold up over time. CUDA and OpenCL, that code's not the same. It gets the job done, but I think in the future those will be building blocks and we'll see higher level programming methods. But those higher level programming methods need more general purpose hardware in my opinion, and that's why I look at CPUs. But I also look at high core count CPUs used in somewhat of an attached processing fashion, and some people will say, oh, that's like a GPU. So I do believe in the idea of having highly scalable systems, and GPUs have helped introduce that to us, the idea that, wow, what could you do if you had a lot of compute power on your desktop? Nobody was going to run out and buy a 10-core CPU just to throw on the desktop, but when they had that, they had a CPU and a GPU, and they experiment with it, they find interesting uses of it, and now that opens the door to these high core count CPUs like Mike.
And when Mike will be shipped, your software compiler, debugger, analysis of program will be fully compatible?
Yes, absolutely. So our Fortran, our C or C++ compiler, our math libraries, our image processing libraries, TBB, everything we have will support Mike as well. And that's one of the benefits of having a x86 processor is the programming models and so forth work. You know, the amount of change needed in our compiler and so forth is very modest, and the ability of a library to be linked to a program running on either Mike or a Xeon CPU it's there automatically because of x86.
And Mike will be first installed on the server side or on the desktop?
I think we'll see. I think the answer to that's server, because I think we'll see it on desktop, but you'll call it a workstation. As soon as you plug this in, it's a workstation, so it's more like a server or a workstation. Yeah, certainly servers, workstations is where we'll see Mike initially. I think one of the reasons is this is going to be a very high performance chip, but it's always going to be a high power chip. And that'll demand a larger system. It won't be going into cell phones anytime soon.
Microsoft works on a new library called Data Parallel Extension for C++, DP++. Do you know this library?
Data Parallel C, yes, absolutely. Data Parallel C++, yes. Microsoft introduced that at supercomputing last fall. Yep.
And have you some advice when this library will be shipped versus your Intel IRBB library? Because it seems your library, IRBB and Data Parallel, are very close about motivation.
Yeah, I think so. Data Parallel C++ is Microsoft working to use their infrastructure and capabilities to allow a program to map onto GPUs. I think it's very early. Definitely have some interest in seeing Microsoft generalize it some more and things, but that'll come in time. Right now, I think that there's multiple things in flight. Our array building blocks has a similar goal, except I think we're much more mathematically oriented, and we're trying to spread across GPUs, Mike, and CPU. At this point, Data Parallel C++ seems to be very focused on specifically on the GPUs. It has some limited CPU capabilities. We'll have to see about Mike in the future. I think there's other programming methods that are direct, like some of the stuff we're doing in Fortran or in C and C++. We'll do some offload models for Mike that I think will have a lot of appeal to people and may fit into existing programs better. But I think we're at a stage now where there's going to be a lot of diversity in different programming methods. I have some technical concerns about data parallel C++, but in the past you can have technical concerns about things and they may come to pass. At this point, Microsoft is taking an approach that is pretty GPU-centric and leans on DirectX very heavily. And I think that'll map very well to a certain set of problems, and I think array building blocks and some of our techniques will be a superior solution for some customers. But I'm just excited to see all this available and looking for customer feedback on all of it, and we'll learn from it.
A general question. In your view, what will Intel and Microsoft bring to the parallel developer for the future? Because I know you work very closely, and I suppose the future will be built on your solution and Microsoft's solution.
Right. Well, I value working with Microsoft. We work with the open source community in Linux. We work with Apple. We've got a lot of companies. But when we work with Microsoft, the value there is that the Windows environment has a lot of richness to it now for parallelism, solutions from Microsoft and Intel. And I think our biggest gift working together is that our solutions work together. So if you use some soft solutions from Intel and Microsoft in the same application, it just works. We've really emphasized that because we believe parallel programming is the future of programming. As I said before, the most common parallel programmer doesn't view themselves as a parallel programmer. They're a programmer that uses some parallelism. Well, we ought to make that easy. And Microsoft and Intel, we believe that, and we have great conversations. And we don't always agree on exactly what the future will be, exactly how the parallel programming will happen. But we agree that as we explore that they ought to sit on common basis, things like concurrency, runtime, and coordinate, and so that they just work together. So if you use Intel's math kernel library, which is based on our OpenMP underneath, and you mix that with Microsoft's PPL, it just works. There's no reason for these things to not work together. It's pretty technically complex to all the things we've done to make them work together. It's just a lot of careful coordination that I would say is difficult inside one company. It gets more difficult if you've got multiple companies working on it. But we've not only set a way for Intel and Microsoft to work together, but we've documented what we've done so that other companies building tools can follow and be equally compatible with our solutions. The other thing that's going to happen is, in a quote Burton Smith from Microsoft, one of their fellows, there's going to be a shift in operating system. Today, an operating system's primary job is to multiplex lots of work to be done onto a few cores. In the future, there's going to be so many cores, the problem's going to be partitioning. Giving an application part of the machine and dedicating it. And we already see this on supercomputers. If you have 10,000 cores out there, an application might be given 1,000 to run on, another one given 3,000. You don't put them on the same cores to operate. And so similarly, we can expect to see an evolution in all operating systems, including Windows. So I'm very excited, looking forward, Windows 8, Windows 9, it's not all going to happen at once, but what we'll see is a tendency, a trend there. So we understand that, the programming methods, the models, the tools, and the operating system are all evolving towards a future with many more cores. And that'll come both in multi-core processors and many-core, like our mic processor. And this abundance of cores is going to change not only the programming models and tools, but the operating system too. And I know we see that same future together with colleagues at Microsoft that I work with, and I firmly believe that is the future.
So you can say the many core is here.
Yes, lots and lots of cores. Yep.
So thank you very much. I appreciate this kind of event to have the chance to discuss with you, and I hope to see you next year. Thank you very much.
Thank you.